Hi students, welcome in the chemistry classes. I am Priyanka Jain and you are watching videos of analytical chemistry. As you know, every Saturday I open a video in the English and every Tuesday I open a video in Hindi so that you can get both the Hindi and the English videos simultaneously. Okay. So today is English Viewers Day. Today we are seeing the English video. Okay, and this video is for the analytical chemistry. I have made several videos on the analytical chemistry before. You can see our playlist of analytical chemistry and several others playlists in the English are also available, so you can see that also. Okay, your exam is very near and a very best wishes to all of you for your exam. Right, so see here, what is column chromatography? In column chromatography, as you have studied about the chromatography in my earlier lecture, I have told you there are several techniques that are used in the chromatography like adsorption, like partition, and one of this is column. Whenever we are using column to separate out the components, this technique will be called a column chromatography. In column chromatography, generally we are taking a column like this. Okay, this type of column we will use here. Okay, so here the separation is done in a column. In column chromatography, the stationary phase is generally solid and the mobile phase is a liquid. Most commonly, if you are seeing the stationary phase, most commonly we use the silica gel or alumina as the solid phase. Okay, so in stationary phase, our phase is either a silica gel or alumina. So first of all, what we have to see? We have to see the column packing, how the column is packed. Okay. So in column chromatography, what you will see? Firstly, we are taking a column like this. Okay. And then this is the column and this will be the stopper like this. This is the stopper. Okay. And here we put a cotton plug. This is the cotton plug. And then we add a little amount of sand. This will be the sand. Okay. In this way here the sand is filled. Why we are filling here the sand? Because sand is inert. It does not react with the sample or with the silica gel. So we are introducing here the sand. And another work of sand is that it will maintain the uniformity of the stationary phase. The uniformity of stationary phase means stationary phase will not move. It will remain as it is. Okay. And now after placing here the sand, we are adding here the stationary phase. Okay. So we are adding here the stationary phase. This will be our stationary phase. Actually it is solid, so we are showing it like this. This is our stationary phase. This may be silica gel or this may be alumina. In more general cases, we are using silica gel here. And then after packing this column, this is the column packing. Firstly, we have introduced here a cotton plug. Then we have filled sand and then we have packed the column with the silica gel. And then at the top of the column, we are placing sample as a narrow band. This will be present in the form of a band. Right. Now, the next thing is the mobile phase. The mobile phase, one of the important thing. What is mobile phase? I have already told you about this in my previous lecture. There are two phases, stationary phase that will remain as it is and mobile phase that we are pouring from here. Okay, we are pouring there the mobile phase. This may be any liquid, but actually one thing you should remember that in column chromatography, the stationary phase and the mobile phase are opposite in nature. What is meaning of it? It means if we are taking the stationary phase polar, suppose our stationary phase is polar, then our mobile phase will be non-polar. And if our mobile phase is polar, then our stationary phase will be non-polar. It means we cannot take both the things of the same type. Why? Because we have to see the separation of the samples. Some samples will have more affinity for the polar phase and some will have less affinity for the polar phase. So we can separate out them by using this stationary phase and mobile phase of opposite nature. Suppose we are taking the silica gel as the stationary phase. As we have seen here, if we are taking silica gel as the stationary phase, then our mobile phase can be CCl4. Okay, if we are using silica gel as the solid phase, then our mobile phase will be carbon tetrachloride. Now what happens as the samples moves down? We are pouring here the sample and now we are adding here the mobile phase. Okay, so what will happen? This sample will go from here. Okay, this will go in this manner, moves the column, And what will happen? The solute begins to separate out and the individual solute bands begin to broaden. Yeah, here you will see different types of the bands. Okay, in this manner you will see the bands. Here the bands will appear out. These are the bands. Once you have poured the sample, this will go down and you will see the bands. And then we can use them and then we can separate out them by using the stopper. The separated out solutions are called eluent. Okay, these that we are getting out from here is called eluent. Okay, and this process of separating out of the eluents is called elution. So basically elution may be of two types. One is called the isocratic illusion. Isocratic illusion means the composition of mobile phase remains constant throughout the process. And second will be called gradient illusion. In gradient illusion, the composition of mobile phase is altered. Now there is a detector that is present at the end of the column. With the help of the detector, we can find out the progress of this chromatographic separation technique. Okay, a plot of detector signals as a function of time or volume of eluted mobile phase is known as the chromatogram. Okay, so what is chromatogram? Chromatogram is a plot of detector signal as a function of time or volume of eluted mobile phase. This is called chromatogram. There are some more important things that you should know about the chromatography, column chromatography. One of the important term here used is retention time. Retention time is denoted by TR. Okay. What is meaning of retention time? The time of solute to move from the point of injection to detector. Suppose this is our column. Okay. This is our column. Okay. And here we have introduced our sample. This is our sample introduced. Okay. So this sample is coming out from here. Okay. And here is the detector. This is our detector. Okay. So the time the solute takes to come from here to here, this time is called the retention time and it is shown by TR. Another important term here is the baseline width. What is baseline width? That is the width of solute's chromatographic band at the baseline. This we will show by W. Okay. Suppose this is our chromatogram and here are two peaks. See here. One peak is here and another peak will be like this. Right. So the width of this at the base, this width is called the baseline width. Okay. And the time taken from here to here will be called the retention time. Okay. And the time taken for the unretained solute to move here will be called this Tm. Tm means void time. This will be called void time. We represent it by Tm and this is the time required for unretained solute to move from point of injection to detector. It means any species that is unretained, that is not being adsorbed and it passes through the column from the point of injection to the detector. Whatever the time it takes will be called the void time. And this is shown here. This is small peak that is for unretained solute and this time here is called the void time. Okay. Now there is one more important term that is called the resolution. Okay, so you can be asked about the numerical from the resolution. Actually, it is the quantitative measure of degree of separation of two chromatographic peaks A and B. Okay, if two solutes are being separated and for them we are getting two peaks. One is A peak, another one is B peak. Okay, suppose we are getting here two peaks like this. This is one peak and this is another peak. This is A peak and this is B peak. Okay. And for their separation, the degree of separation between them is called the resolution. And there is one formula for resolution that you should learn. 2 delta TR divided by WB plus WA. Okay. So this formula you should remember so that you can find out the resolution value. Now the next term is the column selectivity. The relative selectivity of a chromatographic column is given by a selectivity factor that is called alpha. Alpha is equal to KB dash upon Ka. Okay, so this is actually Tr of B minus Tm divided by Tr of A minus Tm. Okay, so by this we can find out the column selectivity. How much selectivity is for one type of the solute. Okay, you can find out with the help of this formula. Next thing is the column efficiency. Actually, at the beginning of a chromatographic separation technique, the solute occupies a narrow band of finite width. As the solute passes through the column, the width of its band continues to increase. Okay, so this is called the broadening. Okay, and column efficiency provides a quantitative measure of the extent of band broadening. So actually we use the column efficiency, we use a term here, that is number of theoretical plates. In the terms of number of theoretical plates, we can find out the column efficiency. So column efficiency is nothing, it is only the number of the theoretical plates. What is theoretical plate? Theoretical plates, actually it is nothing, it is the term that is used for column efficiency, and we use what is theoretical plate. Actually, theoretical plate is a quantitative means of evaluating column efficiency that treats the column as though it consists of a series of small zones or plates. It means, suppose we have given a column like this. I am making just here roughly, you can see it in the books. In books you have given whole types of diagrams, right? So when we are using this type of column, we assume that it is made up of a number of plates. Okay, we are assuming that it is consisting of a number of plates. So these plates, in which in between them the partitioning of the mobile and the stationary phases is occurring. Okay, here the partitioning between the mobile and the stationary phases is occurring. These plates are called the theoretical plates. Actually these are not available, just we are assuming them, so we are calling them theoretical plates. Okay, and the what is the formula for this? N is equal to L upon H. Here L will be the length of column, and H is the height of theoretical plate. Right? There is one more formula that is more applicable. N is equal to 16 Tr upon W whole square. Okay. So you can also use this formula for finding out the theoretical plates. You know about the Tr. Tr is the retention time. W is the baseline width. So you know both the things, and you can find out the number of the theoretical plates. Okay. So this is whole about the column chromatography. Whatever is needed to you, whatever is important, I have told you all the things, all the formulas. I hope you will like this video. And if you are liking these videos, please comment me. Please like the channel. Please share our videos. Thank you.